Good evening, and welcome back to another night of shared adventures. Tonight we drift along the river of stars and gather 100 sleepy facts about the Milky Way, told slowly and faithfully. Settle in and let the night sky become a map. The Milky Way is a barred spiral galaxy within the local group, a community of galaxies bound by gravity. Our home star circles the center over hundreds of millions of years, carrying Earth through a changing view of arms and clusters and streams. If you like these stories, please subscribe and comment to help others find this channel. Now take a breath, rest your eyes, and let us begin. The Milky Way is the pale river that crosses the sky, a barred spiral galaxy in the local group, a great city of suns gently rotating under the governance of gravity. If you could rise above the disk and see it all at once, you would find a shining wheel with a slender bar through its heart and arms that curl outward like luminous pathways. The whole disk is on the order of 100,000 light years from rim to rim, although the most distant stars and gas reach farther into a quiet halo. The main disk is thin in proportion to its width, a few hundred light years thick, where star formation is most active, with a thicker, more diffuse layer above and below that stretches for a few thousand light years. Near the edge, the disk flares, as if the rim of the stellar city relaxes into space. The outer parts are not perfectly flat. They are gently warped, a sign that the galaxy has been nudged by companions and by the pull of its own dark halo. Our sun lives in a small spur called the Orion Arm, between two larger arms that carry many young clusters and bright nebulae. The sun sits about 27,000 light years from the galactic center, far enough out to enjoy a quiet neighborhood, close enough in to feel the full cadence of the galaxy's rotation. The sun orbits the center at a few hundred kilometers each second, a speed that would carry you around Earth many times in a heartbeat. Yet in the galaxy, this is calm and orderly motion. One full orbit takes something like 220 to 250 million years. A single cosmic year is long enough for mountains to rise and fall, for oceans to shift their coasts, for life to change its face many times over. Our species has taken only a fraction of a step on that long path. The center of the Milky Way is not empty. It is a crowded old district filled with ancient stars, dense clusters, and intricate lanes of gas. At the very heart sits a supermassive black hole known as Sagittarius A star. Its mass is about 4 million times that of the Sun, a number read from the graceful orbits of nearby stars that swing past like comets around a campfire. The black hole is quiet by the standards of the most violent galactic centers in the universe. It sips rather than feasts, yet the mass it holds anchors the swirl of the innermost stars and gives a steady point for the whole central region to turn around. Threaded through the center is a bar of stars that spans many thousands of light years. This bar is a kind of traffic system. It stirs gas, directs it inward, and helps shape the spiral arms that unwind from its ends. The bulge around the bar is box-shaped when seen from the side, and in its light live many older stars, rich in the memory of the early galaxy. From the ends of the bar, the arms sweep away. Astronomers give them names to keep their map clear. A major arm lies farther out beyond us. Another reaches inward and across, and many smaller spurs and branches link them like side streets. The exact count of arms is less important than the pattern itself. The density waves that move through the disk gather gas, compress it, and promote the birth of stars. The arms are not rigid bridges, but regions of traffic where newborn clusters linger long enough to light the way. Inside the arms and between them is the interstellar medium, the tenuous substance from which stars are made and to which they return their ashes. Most of this gas is hydrogen. In its atomic form, it whispers at a radio wavelength of 21 centimeters, a line that lets astronomers trace the wide lanes of gas, even through the dust that hides the inner galaxy from our eyes. In its molecular form, hydrogen pairs up and settles into cold, dense clouds. We do not see the hydrogen molecule easily, so we often follow carbon monoxide, a tracer that glows in the radio and points to the places where molecules gather. Inside those clouds, gravity patiently works. Dust grains and gas condense, spin into filaments and knots, and the first sparks of new stars kindle within. Around hot young stars, the gas becomes ionized and shines in soft pink and blue light, sculpted into arcs and pillars by the pressure of starlight and wind. The star-forming regions are nurseries with many cradles. They shine for a time and then disperse when their brightest children explode and blow the walls away. Dust is a small but powerful ingredient of the medium. It is made of tiny grains of carbon and silicates and coated by ice in the coldest places. Dust dims and reddens starlight. It hides the center of the galaxy from a simple glance. It also cools gas, provides surfaces for molecules to form, and collects into the disks that encircle newborn stars. From such dusty disks, planets grow. In this way, the Milky Way is not only a system of stars, but a foundry of worlds. The disk turns, and new systems ignite everywhere, each with its own sky, each with its own future. The galaxy is not quiet in every corner. Supernovae detonate like brief suns and leave behind expanding shells that sweep up gas and dust. These shells run into one another and punch pathways through the disk. There are giant chimneys that vent material into the space above and below the plane. There are bubbles so large that they hold entire constellations. Cosmic rays, which are high-energy particles, race through this structure and help to heat and ionize the gas. The entire disk is threaded by magnetic fields measured in millionths of the strength of a refrigerator magnet. These fields guide charged particles and help shape the filaments and loops we see in radio images. In the grand sum of forces, gravity is the conductor, but magnetism and pressure keep a lively rhythm. The number of stars within the Milky Way is large enough to make any count feel like poetry. A comfortable estimate sits in the hundreds of billions. Some studies suggest a few 100 billion. Some favor a little less or a little more. The exact figure depends on how faint the smallest stars are and how much mass hides in the darkest corners. What matters most for our night is the picture of abundance. Everywhere you look in the disk, stars are born, grow old, and drift along the lanes set by gravity. Many stars travel together for a while in open clusters, gentle gatherings that slowly dissolve as the tides of the galaxy pull them apart. Far beyond the disk, like lanterns hung in a great hall, lie the globular clusters. These are dense spheres of ancient stars, more than 100 of them, each holding the memory of the galaxy's early times in their chemistry and their orbits. Spin a little farther outward in your mind, and you come to the halo, a wide and faint spheroid of stars and dark matter that envelops the disk. The visible halo holds old stars and clusters. The invisible halo is something else. It is made of a substance that does not shine and that passes through light without a trace. We do not yet know its nature, but we know its pull. The way stars and gas orbit the center tells us that the mass of the galaxy is far greater than what we see. The rotation curve is nearly flat across much of the disk rather than falling away in the outer parts. This is the signature of a halo that holds the galaxy in a wider embrace. A reasonable estimate places the total mass of the Milky Way around 1 trillion times the mass of the Sun. The dark matter halo is the scaffolding that allowed the disk to form and that now steadies its rotation. Within the disk, the pace of star birth is neither frantic nor sleepy. On average, the Milky Way turns something like 1 or 2 suns worth of gas into stars each year. That number hides the real story, which is patchy and episodic. Some regions are crackling with activity as shocks and spiral waves focus gas into clouds. Other regions are quiet as the gas there has been used up or blown away. Over long time scales, this birth rate declines as fuel is consumed, even as fresh gas trickles in from the halo and from the small companions that share our sky. To map all of this structure, astronomers reach for many tools. Distance is the hardest thing in the sky to measure, so we build ladders of measurement. Pulsating stars called Cepheids and RR Lyrae serve as standard candles whose periods reveal their true brightness. When their observed brightness is compared to that truth, their distances fall out of the arithmetic. Mazes in star-forming regions act like beacons that can be measured exquisitely by radio arrays, fixing the spacing of spiral arms and the size of the bar. Infrared surveys slip through the dust and reveal the crowded heart of the bulge. Radio telescopes follow hydrogen all through the disk, turning the sky into a weather map of clouds and streams. And astrometric missions measure the positions and motions of more than 1 billion stars with exquisite precision. From these motions, one can watch the galaxy still in formation, see the signatures of past encounters, and calibrate the rotation of the whole disk. The Milky Way is not just a structure. It is a place with neighborhoods and signs, with districts of character and quiet cul-de-sacs, where a planetary system can drift in peace. Near the Sun is a region of low density called the local bubble, carved long ago by supernovae whose shock fronts pushed gas aside and left a cavity of warm, thin plasma. The Sun rides one side of this bubble and peeks into others, as many such cavities fill the disk like a foam. Nearby are associations of young stars that share a common origin. Traces of older supernovae ride the magnetic field and sprinkle Earth with rare isotopes that sometimes leave marks in ocean sediments. Even in the calmest neighborhood, there are messages that the galaxy is alive and in motion. Take a moment to picture the different kinds of stars that populate this city. The youngest and most massive are blue and brilliant, short-lived and quick to enrich their surroundings when they die. The most common are small red dwarfs that glow softly for trillions of years, so long that the universe has not yet aged enough for any of them to have grown old. Between those extremes lie stars like the Sun, steady and middle-aged. When such stars exhaust the hydrogen in their cores, they swell into red giants and shed their outer layers into delicate shells. The cores cool into white dwarfs that will fade for ages longer than any word we have for time. The mix of stellar ages and types changes with position. The inner regions are richer in heavy elements because many generations of stars have lived and died there. The outer disk is more pristine, and the halo is a museum of ancient low metal stars that record the early chemistry of the galaxy. The arms tell another part of the story. They are not permanent tracks that stars must follow. They are waves of higher density that move through the disk and sweep gas along. As gas is compressed, it triggers star formation, so the arms light up with short-lived blue stars that keep the pattern visible. Farther within each arm, the light turns golden as the older, longer-lived stars gather there. The spacing and pitch of the arms are set by the rotation of the disk and by the presence of the central bar. Where arms intersect, or where gas piles up at the ends of the bar, great complexes of molecular clouds form. In those complexes, In caverns of dust and cold, thousands of stars are born. You can imagine wandering along one such arm on a quiet night. You pass an open cluster that will disperse in a few 100 million years. You pass a cradle of stars wrapped in dark lanes like a shawl. You pass an old red giant that has sown carbon into the wind. Everywhere there are signs that the galaxy is at work, making light and structure from simple elements. Hydrogen and helium were the first notes. Through the burning hearts of stars came carbon and oxygen and the iron that anchors the cores of rocky planets. From the lives and deaths of stars came the ingredients for oceans and clouds and the chemistry that can think about itself. Above and below the thin, bright lane of the disk, there is a population of stars that drift in wider orbits. This thick disk holds stars that are, on average, older and poorer in heavy elements. Their kinematics betray a more turbulent past, when the galaxy was younger and mergers were more common. Beyond that, in the halo, distant streams of stars trace the remains of small galaxies that fell in long ago. These streams show that the Milky Way has grown by accretion and that its present shape is the result of many quiet collisions and tidal dances. Even without naming each event, the architecture tells the tale. The disk is settled, the bar is strong, the arms are fed, and the halo is peppered with the fossils of assembly. Our galaxy is also embedded in a corona of hot gas that extends for hundreds of thousands of light years. This gas is difficult to see directly, but its presence is inferred from the way it absorbs and emits X-rays and from the way it slows high-velocity clouds that fall toward the disk. The corona is a reservoir from which the disk can draw a slow rain of material. It also helps to explain why the outermost parts of the galaxy are more complex than a simple picture would predict. The disk exchanges matter and energy with this halo constantly. Star formation and supernovae push gas out. Cooling and gravity bring it back in. When you step back and consider the Milky Way as a whole, a pattern emerges that is both simple and profound. Gravity gathered dark matter into a halo. Baryons in the form of gas fell into that potential well, cooled and settled into a rotating disk. Cosmic time and rotation set the table for a bar and for spiral structure. Stars formed, lived, and died, changing the chemistry of the gas and the opacity of the disk. Small companions brought streams and nudges that warped the outer parts and fed the arms. Magnetic fields and cosmic rays threading the medium added texture to the flow. The product of all these processes is the luminous structure that stretches across our night. From the vantage of Earth, we see only a thin slice through this grandeur. The band we call the Milky Way is the sum of countless lines of sight through the disk. In summer, we face toward the center, and the sky is rich with star clouds and dark rifts. In winter, we turn outward, and the band is thinner and sharper. Through binoculars, the mist resolves into stars. Through a radio dish, the mist resolves into maps of hydrogen. Through infrared detectors, the dust lifts and the bulge appears. With precise astrometry, the star fields turn into a choreographed dance whose steps tell us the true shape of the floor beneath. The purpose of this first part of our night is simple. It is to understand how the Milky Way is put together, a barred spiral galaxy with a thin bright disk and a thick companion layer, a central bar, and a box-shaped bulge around a black hole of 4 million solar masses, several spiral arms that are patterns of compression and star birth rather than solid spirals of stars, a warped and flared outer disk, a population of hundreds of billions of stars with many ages and chemistries, a medium of hydrogen in atomic and molecular and ionized forms, threaded by magnetic fields and shaped by the explosions of massive stars, a halo of ancient clusters and streams, embraced by a vast dark matter halo that keeps the rotation curve nearly flat, a star formation rate of about 1 or 2 suns each year, a sun that rides a quiet path in a small spur, circling the center on a journey that will last longer than empires and languages, and perhaps longer than memory itself. The Milky Way was not born mature. It gathered itself from the faint mist of the early universe when gravity began to tease ripples in the primordial sea of hydrogen and helium. In those first billions of years, gas fell inward and spun into a young rotating disk. The earliest stars were poor in heavy elements, since only hydrogen and helium were abundant at the start. Their light is fossil light, carrying the simple chemistry of a universe just beginning to write new elements in its furnaces. From such beginnings, the galaxy slowly layered itself into the architecture we see today, with a thick disk of older stars that drift above and below the midplane, and a thinner, brighter disk of younger populations closer to the heart of the rotation. The story of that layering lives in the chemistry of stars. Astronomers measure the abundance of elements heavier than helium and find a pattern that changes with both age and location. Older stars, especially those of the halo and thick disk, tend to be metal poor, a phrase that means only that they were born before many cycles of stellar alchemy had enriched the gas. Younger stars near the inner disk show higher metallicity, a sign that many generations have lived and died there, seeding the interstellar medium with carbon, oxygen, silicon, and iron. There is a gentle gradient across the disk. The farther one travels outward from the center, the lower the average metallicity becomes. This is a chemical memory of how star formation has been more sustained in the inner regions than at the edge, and how fresh, less enriched gas has continued to settle onto the outer disk. The galaxy carries scars of encounters. Several times in its long life, the Milky Way has met and absorbed smaller companions. One major event is remembered in the orbits of stars that stream through the halo on elongated paths. This debris is connected with a long-ago collision, often called Gaia Enceladus. The motions and chemistry of those stars suggest an encounter that took place roughly 10 billion years ago, an event large enough to heat the early disk and help create the thicker component we observe today. Another companion, the Sagittarius dwarf galaxy, is still being torn apart. Its stars trace looping streams around the Milky Way, while its repeated passages through the disk may have stirred gas and even helped to shape the bar. Farther out, rings of stars, such as the monoceros structure, hint at additional accretion in the outskirts. Each stream is a line in the ledger of growth, a reminder that a galaxy does not stand alone but grows by gathering what wanders too near. At the true center, where the bulge is densest and dustiest, a compact object sits as steady as a metronome for the orbits around it. This is Sagittarius, a star, a supermassive black hole with a mass of about 4 million suns. We know its mass, not by theory alone, but by watching the paths of individual stars that whip through the central tenths of a parsec on tight ellipses. These orbits complete in years to decades, and their speeds reveal the gravity that holds them. Sagittarius. A star is quiescent by the standards of active galactic nuclei. It accretes little and shines faintly compared with the great beacons in distant galaxies. Yet its presence anchors the nucleus star cluster, a crowded neighborhood where stars are born, age, and sometimes meet fates, unlike those in calmer districts. Around this nucleus lies the central molecular zone, a ring and web of dense clouds that circle the heart and feed sporadic star formation. Beyond the immediate center rise two large lobes that extend above and below the galactic plane. These are known as the galactic bubbles, seen in gamma rays and traced also in X-rays and radio. Their edges are crisp and their interiors glow with energetic particles. Their origin remains under study. They may be the relics of a burst of star formation in the central regions a few million years ago, or the afterglow of a period when the black hole accreted more vigorously and drove twin outflows. Either way, they show that the Milky Way has a history of feedback, a word astronomers use to mean the return of energy from stars and black holes into the gas that surrounds them. That energy shapes the halo, accelerates cosmic rays, and regulates the rate at which the disk can continue to form new stars. Star birth itself is a quiet miracle repeated on great scales. Within the cold shadows of molecular clouds, gravity overcomes pressure in clumps and filaments. Those clumps collapse, heat their centers, and ignite nuclear fusion. A star is born. Around many young stars, disks of dust and gas turn and flatten. In time, these disks assemble planets, moons, and debris belts. The rate at which the Milky Way transforms gas into stars is on the order of 1 or 2 solar masses each year. Some years and places are busier than others. Spiral density waves, collisions of clouds, and shocks from older stellar winds all help to trigger new clusters. The youngest and most massive stars live fast and brighten their surroundings. They carve cavities, ionize vast regions, and then end in supernova explosions that seed the gas with heavy elements and send shock fronts that can compress nearby material into new generations. The endings of stars are as informative as their beginnings. A star like the Sun will eventually shed its outer layers as a glowing shell that expands into space, while its core settles as a white dwarf that cools very slowly. More massive stars die in core collapse. When the core can no longer support itself, it falls inward and a supernova follows. The remnant becomes a neutron star or a black hole, and the surrounding space is enriched with elements forged in the heat of the blast. On rarer occasions, the merger of 2 neutron stars will produce a short burst of gamma rays and a kilonova whose light carries the signature of newly created heavy elements like gold and platinum. All of these processes contribute to the chemical evolution of the galaxy, and their rates and yields are written in the spectrum of stars and gas. The Milky Way experiences supernovae a few times per century on average. Many are hidden from optical view by dust in the plane, but their traces can be found in radio and X-ray maps as shells and filaments that still glow centuries later. These remnants sweep gas into arcs, stir magnetic fields, and add high-energy particles to the cosmic ray population. The combined effect of many explosions can excavate superbubbles that span hundreds of light years and connect to chimneys that carry hot gas into the halo. In this way, the disk and the halo trade matter and energy, a cycle that balances the pace of star formation and keeps the interstellar medium multi-phased, with cold, densest regions embedded within a warmer and hotter background. Not all stars are equal in age, nor are they distributed randomly in time. The thick disk holds a greater share of older, kinematically warmer stars. The thin disk is younger on average, with a continuous history of formation that has ebbed and flowed over billions of years. The bulge, with its boxy shape, contains both ancient populations and a component that appears to have formed through the evolution of the central bar, where orbits crowd and scatter stars into a puffed-up structure. Globular clusters, most of them more than 10 billion years old, orbit in the halo as compact museums of early stellar chemistry. Their orbits and spatial distribution are guides to the assembly history of the outer galaxy. Each cluster's stars share a narrow age range, making them clocks that help to date the stages of galactic growth. Our neighborhood bears the imprint of past activity as well. The sun presently moves within the local bubble, a cavity of low-density gas some hundreds of light-years across. Its walls are rich in dust and young stars, and its interior is warmer and thinner than the average interstellar medium. Multiple supernovae in nearby associations likely created this cavity over the past 10 to 20 million years. The sun's path through such regions changes the local conditions around the heliosphere, the wind-blown bubble made by the sun itself, and so affects the environment through which the planets travel. Nearby associations of young stars, such as those in Scorpius and Centaurus, host clusters and remnants that help map this recent history. The magnetic character of the Milky Way also evolves. Galactic magnetic fields on large scales follow the spiral geometry of the disk, while on smaller scales turbulence and feedback tangle the lines. Polarized radio emission and the Faraday rotation of background sources reveal the strength and direction of these fields. They are weak by everyday standards, yet they influence the structure of clouds, the diffusion of cosmic rays, and the shapes of supernova remnants. Combined with gravity, rotation, pressure, and radiation, magnetic fields participate in the long conversation that decides where and when the next stars will light. The ongoing life of the galaxy is a balance of supply and demand. Gas is consumed by star formation and returned by stellar winds and deaths. Fresh material arrives from the halo and from small companions whose gas is stripped and added to the disk. High-velocity clouds fall inward and are slowed by the hot corona, mixing as they come. The bar helps funnel gas toward the center, where it can build dense clouds in the nuclear environment. Spiral arms maintain a patterned speed that constantly reorganizes the interstellar medium. All of this proceeds over timescales far beyond a human life, yet each process leaves signatures that can be read today. Time has also shaped the orbits of stars. Resonances with the bar and with spiral patterns scatter them, tilting and heating their motions. Encounters with giant molecular clouds nudge paths and slowly thicken the disk. Over billions of years, these small changes accumulate. The Milky Way we inhabit now is not exactly the one that set its first stars shining. It carries within it the results of countless small adjustments and a few grand events. From its earliest collapse to its present arrangement, the galaxy has been a place of steady transformation, governed by known physics and traced by starlight. In the heart, in the bulge and bar, in the nuclear cluster around Sagittarius, a star, the pace of change is fastest. Orbits are crowded, tides are strong, and gas flows are complex. Stars there display a wide range of ages, and the chemistry indicates both ancient formation and later secular growth driven by the bar. The quietness of the central black hole today does not preclude episodes of greater activity in the past. Echoes of brighter times may linger in the variability of X-ray reflection from nearby molecular clouds, a kind of time-delayed record of flares that lit the center centuries ago. Such clues continue to be gathered as new instruments sharpen our view through the veils of dust. The history, the heart, and the ongoing life of the Milky Way are inseparable. Age reveals itself through chemistry and motion, merges right rivers of stars across the halo. The center holds a massive black hole whose gravity shapes the nucleus. Energetic structures carry the memory of outbursts. Stars are born, live, and end in a cycle that enriches the gas and regulates the future rate of formation. Magnetic fields and cosmic rays add texture to the play of forces. The disk and halo exchange matter. The present is only a frame in a very long film, but it is a frame we can read with clarity. The Milky Way keeps company. Around the bright disk and bulge there moves a retinue of small galaxies, each a story of its own. The largest companions are the large and small Magellanic Clouds, visible in southern skies as pale islands of light. They are irregular systems rich in gas and star formation, and they tug on one another while they circle our galaxy. Between them lies a bridge of gas, and trailing behind them is a long stream of hydrogen that arcs across the sky. Gravity writes these structures as the clouds feel the pull of the Milky Way and of each other. Many fainter companions also share our neighborhood. Dozens of dwarf spheroidal galaxies and star-rich fragments orbit in the halo, some only recently revealed by deep surveys. Their stars are old and their gas is meager, yet their presence matters. They feed the halo with streams and aid our understanding of how large galaxies assemble from smaller building blocks. Beyond our satellites lies the wider family called the local group. It is a modest association by cosmic standards, but to us it is the sea in which our island floats. The most massive members are the Milky Way and the Andromeda Galaxy, with the Triangulum Galaxy as a smaller spiral nearby. Each of these brings its own satellites, and together they form a loose-bound system, spread across a span of a few million light-years. The local group itself sits within a broader structure known as the local sheet, a gently flattened arrangement of galaxies that share similar motions. Farther still, our region belongs to a vast assembly called the Laniakea supercluster, a network of filaments and clusters where gravity guides the slow rivers of galaxies toward regions of higher density. These grand scales set the stage for the motions we measure close to home, and they remind us that a galaxy is both a world unto itself and a citizen of a larger cosmos. The approach of Andromeda is one of the most telling facts about our future. Careful measurements show that the Andromeda Galaxy is moving toward the Milky Way, and that in a few billion years the two will meet. The The first passage will stir long tidal bridges and tails of stars. The disks will distort, gas will be shocked and compressed, and a new rash of star formation will follow in many places. After several close encounters, the two systems will merge into a single remnant that will likely be an enormous elliptical-like galaxy with a bright core and wide wings of stars. Direct collisions between individual stars will remain rare because stars are small compared with the distances between them, but orbits will change and many clusters will be scattered to new homes. The central black holes will spiral inward through the sea of stars and gas and eventually coalesce, releasing a burst of gravitational waves that will ring through space. By the time of the final union, the Sun will be entering the late chapters of its life, and our local sky will be unfamiliar but still governed by the same laws. To map these motions and to place numbers on these scenarios, astronomers continue to improve their measures of distance and speed. Astrometric missions make a living atlas of the Milky Way and its neighbors, fixing positions and charting proper motions with precision. Spectrographs read the Doppler shift of stars and gas to give radial speeds. Long baseline radio arrays pinpoint mazes in star-forming regions and in the centers of galaxies, yielding distances with exquisite accuracy. The three-dimensional map that results shows not only where the stars are, but where they are going. In that dance we see the signatures of past accretion, of the pull of the central bar, and of the tide that draws us and Andromeda together. The sky around us also carries the marks of travelers that do not belong to any one system. There are hypervelocity stars that race outward fast enough to escape the Milky Way. Some are ejected when a close binary meets the deep gravity of the central black hole, and one star is flung away while the other is captured. Others are runaways launched by the explosion of a companion. Their paths are test particles in the galactic potential, and their chemistry preserves the history of the regions that launch them. There are also high-velocity clouds of gas that fall toward the disk from the halo. As they move through the hot corona that surrounds the galaxy, they are slowed and warmed, and some of their material mixes into the outer layers of the disk, adding fresh fuel to future star formation. The corona itself is a quiet giant. It is a vast sphere of thin, very hot gas that envelopes the Milky Way for hundreds of thousands of light years. It is seen indirectly through the way it absorbs and emits X-rays, and through the shadows it casts on the light of distant background sources. This circumgalactic medium is a significant reservoir of matter. It receives outflows from the disk when star formation and supernovae drive fountains of gas upward, and it returns matter to the disk as cooling and gravity draw the gas back down. This exchange helps regulate the rate at which the galaxy can continue to form stars. It also acts as the medium through which satellites move, stripping their gas through pressure as they plunge through and writing long tails behind them that later fold into the disk as new streams. The Milky Way is rich in worlds. The discovery of planets around other stars has changed a supposition into an observable fact. Our galaxy holds billions upon billions of planets, many smaller than Neptune and many that are rocky. Planets come in a diversity that is larger than our early guesses. Some are hot and near their stars, some are cold and distant, and there are many in between. A working idea called the galactic habitable zone suggests that there is a ring in the disk where heavy elements are sufficient to form rocky planets, and where the rate of cataclysmic events is low enough to allow long, stable epochs. This is not a sharp border, but a way to organize thought about where life could take hold. The presence of planets around stars of all types points to a galaxy that is prolific and patient with the construction of worlds. Our tools for seeing this are varied. Optical surveys catalogue stars and measure their colors and spectra. Infrared missions look through dust and give a clear view of the bulge and the embedded nurseries in the arms. Radio telescopes trace atomic hydrogen through the 21-centimeter line and follow molecular gas through the glow of carbon monoxide and other traces. Submillimeter arrays resolve the coldest dust and the disks where planets grow. X-ray and gamma-ray instruments catch the high-energy signatures of remnants and bubbles and the quiet breathing of the hot halo. Gravitational wave observatories now sense the ripples from collisions of black holes and neutron stars, events that write their signatures on space itself and that confirm the pathways by which heavy elements are built. Each window gives a piece of the whole, and together they turn the Milky Way from a smear of light into a measured structure. Cartography on this scale reaches for traces that act as beacons. Cepheid and RR Lyrae variables continue to provide distances in places where dust allows their light to pass. Red clump giants offer another standard glow. Star clusters with well-understood populations become yardsticks that mark the outlines of arms and the profile of the bulge. Mars's tied to star-forming regions give distances where other methods falter, especially within the first few kiloparsecs of the center where confusion is great. Stellar streams, once only curiosities, now serve as test paths for models of the dark matter halo. By fitting the shape of a stream and the motions of its stars, astronomers infer the shape and clumpiness of the unseen mass that envelopes the galaxy. The neighborhood of the Milky Way in this epoch is also marked by visitors that pass through on their own errands. Interstellar objects that formed around other stars can drift into the inner regions of our system, as happened with the discoveries of an elongated traveler first seen in 2017 and a more typical comet seen in 2019. Such bodies are not bound to the Sun and will return to the wider galaxy, but their brief presence is a reminder that the disk is full of debris that wanders from system to system over great spans of time. The interstellar medium is not empty. It contains dust, molecules, and sometimes the seeds of new stories. On timescales longer than the life of a star like the Sun, the Milky Way will continue to evolve. Gas will be turned into stars at a pace that slowly declines as the supply is used and as the balance of inflow and outflow settles. The outer disk will continue to feel the pull of satellites and streams, and its warp may change as companions pass by. The bar may grow or weaken depending on the distribution of mass in the inner galaxy and on the exchange of angular momentum between stars and dark matter. The halo will keep the rotation curve near flat and will collect the remnants of future small mergers. After the meeting with Andromeda, the combined system will relax into a more rounded form with a hot stellar component and a diffuse envelope. Clusters will sink toward the center through friction with the background of stars. The merged black hole will sit in a core crowded with stars that have been scattered into new orbits. The space beyond the local group will continue to recede as cosmic expansion carries distant structures away faster with increasing distance. Within the gravitationally bound region of the local group, however, the galaxies will remain together. The wider supercluster will become a backdrop, and eventually only the light of the local remnant will fill the sky for any observers that arise on far future worlds within it. The laws of physics that guide this pathway are the same that shape the spiral arms and that hold our planet in its orbit. They connect the motion of a nearby cluster with the flow of galaxies in a filament millions of light years long. The present era is one of measurement and of synthesis. With every new survey, the map sharpens. With every new method, the model of the Milky Way becomes more complete. From satellites bright enough to see with the unaided eye, to dwarfs that are only seen by adding the light of many faint stars together. From streams that loop through the halo to the bridge of gas between the Magellanic Clouds. From the gentle approach of Andromeda to the distant pull of the Virgo cluster and the streams that define Laniakea, our galaxy is placed in context. It is a system with a living edge and a patient heart, linked by gravity to neighbors near and far, and made legible by light that has crossed the dark to reach us.